Have you ever thought that light, something we see every day, holds a secret that has perplexed the greatest scientists for centuries? From warm sunbeams to modern LED lights, light seems like a familiar, easy-to-understand phenomenon. But is it really? Let's explore the journey from the classical perception of light as an ethereal wave to the shocking discovery of its mysterious quantum nature. Welcome to SpaceTime's universe journey of discovery, where we explore the deepest mysteries of the universe. In this video, we will explore light, the quantum nature of a classical phenomenon. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us.
From ancient times, humans have been fascinated by light. But it wasn't until the 17th century that Isaac Newton hypothesized that light was composed of tiny particles called corpuscles. This theory explained many phenomena like reflection and refraction, but struggled to explain interference and diffraction. Later discoveries about the wave nature of light began to reveal the limitations of this view. The debate about the nature of light continued for a long time. Later, Thomas Young, with his famous double-slit experiment, convincingly demonstrated that light clearly exhibits wave properties, creating interference patterns similar to water waves. This experiment dealt a strong blow to Newton's particle theory and ushered in a new era for light physics. This was the foundation for the development of electromagnetic theory. By the mid-19th century, James Clerk Maxwell had unified the laws of electricity and magnetism into a single system of equations, demonstrating that light is, in fact, a form of electromagnetic wave. Maxwell's equations not only predicted the existence of electromagnetic waves, but also calculated their speed, which matched the measured speed of light. This achievement is considered one of the pinnacles of classical physics, firmly reinforcing the view of light as a wave. This also paved the way for technological applications, such as radio and television, completely changing how we communicate and experience the world. Scientists at the time believed that the nature of light had been perfectly and completely resolved. However, in the late 19th and early 20th centuries, a series of mysterious experiments began to challenge this view. Blackbody radiation, the photoelectric effect, and atomic line spectra could not be explained by classical wave theory. This created a crisis in physics, forcing scientists to search for entirely new ideas. The inability of classical physics to solve these problems opened the door to a scientific revolution that we later called quantum mechanics.
Blackbody radiation was one of the first mysteries. Classical physicists predicted that a heated blackbody would emit an infinite amount of radiation at short wavelengths, the so-called ultraviolet catastrophe. However, experimental observations showed a completely different energy distribution. No one could explain this contradiction. This was a major challenge for classical physics, indicating that something fundamental had been overlooked in our understanding of energy. In 1900, German physicist Max Planck put forward a bold hypothesis to explain blackbody radiation. Energy is not emitted or absorbed continuously, but in discrete, tiny packets called quanta. The energy of each quantum is directly proportional to the frequency of the radiation, expressed by the formula E equals hf, where h is Planck's constant. This hypothesis, initially considered a mathematical trick to fit experimental data, laid the foundation for all of quantum mechanics. Planck reluctantly accepted this, but he did not know that his discovery would open up an entirely new field of physics. Then, in 1905, Albert Einstein used Planck's quantum idea to explain the photoelectric effect. This phenomenon occurs when light strikes a metal, ejecting electrons. Classical wave theory could not explain why there was a threshold frequency, below which, no matter how intense the light, electrons would not be ejected. Einstein proposed that light is not only emitted and absorbed as quanta, but is itself composed of quantum particles, later called photons. He demonstrated that each photon carries a specific amount of energy, E equals hf, and only when this energy is large enough to overcome the electron's binding energy in the metal can the electron be ejected.
This was a significant breakthrough. This work not only perfectly explained the photoelectric effect, but also reasserted the particle nature of light, an idea that had long been dismissed. It laid the groundwork for the development of quantum optics and laser technology, opening up unimaginable possibilities for science and engineering. Einstein's discovery caused a major stir in the scientific community. Light, which was thought to be a pure wave, was now considered to consist of particles. This seemed to directly contradict what had been proven about light's wave nature through interference and diffraction experiments. Scientists were faced with a perplexing question: is light ultimately a wave or a particle? This contradiction became the center of a heated debate, not only about the nature of light, but also about how we perceive physical reality. To resolve this paradox, Louis de Broglie in 1924 proposed a revolutionary idea. Not only light has wave-particle duality, but all matter particles, including electrons, protons, and neutrons, also have wave properties. De Broglie's hypothesis unified the seemingly contradictory concepts of waves and particles, extending the principle of wave-particle duality to the entire universe. This discovery opened up a completely new direction in physics, leading to the birth of modern quantum mechanics. It showed that at the most fundamental level, reality is not simply particles or waves, but a complex combination of both.
So, what is the quantum nature of light? Light is neither a wave nor a particle separately. It exhibits both properties depending on how we observe it. In some experiments, light behaves like a wave, for example, interference, while in others, it behaves like a particle, for example, the photoelectric effect. This concept is called wave-particle duality. It is one of the most fundamental and surprising principles of quantum mechanics. It has changed our understanding of the universe at the microscopic level, leading to groundbreaking technologies such as lasers, transistors, and quantum computers, shaping our modern world. Wave-particle duality applies not only to light, but to all fundamental particles, from electrons to protons. Each particle carries both wave and particle characteristics, and how they manifest depends on their interaction with the observation environment. One of the most classic examples to illustrate wave-particle duality is the double-slit experiment with electrons. When electrons are fired through two narrow slits, they create an interference pattern on a screen behind, just like waves. Surprisingly, this phenomenon still occurs even when electrons are fired one at a time. This suggests that each electron passes through both slits and interferes with itself, a concept utterly unimaginable in classical physics. However, if we try to determine which slit the electron passes through, for example by placing a detector, the interference pattern disappears, and the electrons behave as individual particles, passing through one slit or the other. This behavior is called wave function collapse, and it shows that the act of measurement profoundly affects the nature of quantum reality.
This experiment raises deep questions about the nature of reality and the role of the observer. Does matter have a definite nature before being observed,
Or is its nature formed by the act of observation itself? This is one of the most perplexing aspects of quantum mechanics and has led to many intense philosophical debates. It challenges our intuition about the world and forces us to accept a reality far more complex than we ever thought. The double-slit experiment with electrons is not just a physics experiment, but also a profound philosophical question, opening the door to exploring the limits of human knowledge and the fundamental nature of the universe. This experiment shows that reality at the quantum level is not a collection of objects independent of the observer, but a complex network of possibilities that become concrete only when measured. This has profound implications for how we understand the universe, from the smallest particles to the largest structures. From there, it has reshaped how scientists approach physical problems, opening up new avenues of research and unprecedented technological applications. This experiment is not only a milestone in the history of physics, but also a symbol of the mystery and beauty of the quantum world. It continues to inspire scientists and philosophers, urging them to think deeper about the fundamental questions of existence.
This is a powerful testament to the inseparability of the act of observation and the nature of reality at the quantum level. This opens the door to advanced technologies such as quantum computers and quantum communication. It has helped us understand that the world at a fundamental level does not follow the intuitive rules we are familiar with, but operates based on principles of probability and possibility. The double-slit experiment has forever changed how we perceive physics and reality. It has driven the development of many new theories and models, helping us better understand how the universe operates at its most fundamental level. This has opened up new possibilities for creating technology and exploring the limits of physics. The double-slit experiment continues to be one of the most important experiments in the history of science, providing deep insights into the true nature of matter and energy. It has helped us realize that the world is not as simple as we thought, and there are many mysteries waiting to be discovered. The quantum nature of light is not just an abstract concept in physics. It has profound practical applications, from laser technology in medicine and industry to modern electronic devices and fiber optic telecommunications. Lasers, for example, are based on the principle of stimulated emission of photons, allowing the creation of high-intensity, directed and monochromatic light beams, used in everything from metal cutting to eye surgery. This has revolutionized many industries. These applications have significantly changed our daily lives, from smartphones to global positioning systems. Semiconductor technology, the foundation of all modern electronic devices, also depends on an understanding of the quantum interaction between light and matter. From manufacturing minuscule computer chips to developing efficient solar panels, knowledge of photons and electrons is indispensable. A deep understanding of the quantum nature of light has opened the door to creating advanced technologies, completely changing how we live and work. It has driven the development of artificial intelligence, self-driving cars, and many other technologies. This demonstrates the importance of quantum physics research in shaping the future of humanity. Medicine has witnessed tremendous progress thanks to quantum light-based technology. From advanced diagnostic imaging like MRI, magnetic resonance imaging, and PET, positron emission tomography, to laser and photodynamic therapies, light plays a central role. These techniques allow doctors to look deep inside the human body without invasive surgery, helping to detect and treat diseases earlier and more effectively. This has significantly improved the quality of life for millions of people worldwide. This development also opens new avenues of research into how light can interact with living cells to heal diseases.
In communication, fiber optics has revolutionized data transmission, allowing us to send information at the speed of light over very long distances. The operating principle of fiber optics relies on the efficient transmission of photons through ultra-thin glass fibers. This is a direct application of understanding how light interacts with matter at the quantum level. It has created a revolution in communications, connecting the globe and ushering in the era of broadband internet. This development is not only a technical achievement, but also a testament to the power of quantum physics in changing the world. Even emerging technologies like quantum computing and quantum communication are harnessing the quantum nature of light. They use the superposition and entanglement states of photons to perform complex calculations and transmit information securely in ways that classical systems cannot match. These technologies promise to bring profound changes in many fields, from data security to drug development and artificial intelligence. Their potential is immense. This is not only a technical challenge, but also a scientific exploration of the limits of information and computation. However, our understanding of the quantum nature of light still holds many mysteries. Scientists are still trying to reconcile quantum mechanics with Einstein's general relativity, especially under extreme conditions, such as near black holes or in the early stages of the universe. This shows that we still have much to learn about how the universe operates at the most fundamental level. These efforts not only push the boundaries of physics, but also open new doors to understanding the universe and our place within it. These unanswered questions remain a great motivation for further research.
Additionally, concepts like entanglement and quantum teleportation are still being explored. Though they sound like science fiction, these phenomena have been demonstrated in laboratories and promise groundbreaking applications in the future, especially in the field of information and security. This shows that the quantum universe still holds many surprises waiting for us to discover. It opens up incredible possibilities for creating entirely new technologies. The wonder of the quantum world continues to challenge our imagination, pushing us to delve deeper into the mysteries of reality. Our understanding of light, from classical to quantum perspectives, has completely changed our perception of the world. It is not just a physical phenomenon, but also a window into the deep nature of the universe. From a gently flowing river, light has transformed into tiny, constantly dancing and interacting streams of particles, carrying the mysteries and beauty of the quantum world. This journey continues to open new horizons for science. It has helped us realize that what we take for granted harbors wonders and complexities. This has also driven the development of many other scientific fields, from chemistry to biology and medicine. We stand at the threshold of even greater discoveries that will continue to shape the future of humanity and how we perceive ourselves in this vast universe. Light, with its captivating dual nature, remains an endless source of inspiration for scientists and philosophers, continually urging us to seek answers to the biggest questions about reality. Despite significant progress, there is still much about light that we do not fully understand.
Physicists are still searching for a unified theory that can combine both quantum mechanics and general relativity, and light will certainly play an important role in future discoveries. This shows that the journey of scientific exploration never ends, and each answer opens up more new questions, pushing us further in our understanding of the universe. The dual nature of light shows that the universe holds more mysteries than we imagine. But to better understand how this reality is shaped, we need to revisit another fundamental concept, space-time. In our next video, we will explore the historical journey of spacetime from Newton's classical imaginings to Einstein's revolutionary ideas and the mysteries that lie ahead. Stay tuned for video number 29, The History of Spacetime from Newton to Einstein and Beyond, to continue our journey of cosmic discovery.